So now let's look at Chapter 5, Lithography. So historically, lithography is the printing technology that is based on the chemical repellent of oil and water. So photolithography means light, stone, litho, stone, graphy, writing. So in 1826, the French Joseph, he took the first photograph using the basement of Judea on a pewter plate. So what is this? So this is a kind of asphalt. We know the asphalt for the construction. So this material itself, it will be hardened by light. So you shine the light. If you shine the light on this material, it will be hardened. Then you can use developer. The developer is the oil or lavender. This can remove the area without exposure. So that means this resist is a negative resist. So negative resist means exposed area will remain, unexposed area will be gone. So this it is like a resist because it is hardened, solidified, cross-linked by the light. In 1935, Louis from Eastman Kodak, this is the film company, developed the first negative photoresist. And 1940 also developed the first positive photoresist. So this is lithography for the art. So we can use a printing technique. We can do a printing to pattern some area with the hydrophobic chemicals. So some area is hydrophobic chemicals. Then we can put the plate into a ink. So the ink will go to the hydrophobic area. Then in this way we have the image. So the image here, we have the ink. It is hydrophobic. For the IC manufacturing, this is the idea for the IC manufacturing. So we have the photoresist. We shine the light, and we get more soluble or less soluble depending on whether it is a positive resist or negative resist. So here the black color is like chrome. So this is the chrome block the light. So in the IC manufacturing, lithography is the most important technology. So 35% of the manufacturing cost come from the lithography. And the lithography equipment is also very expensive. So the state of art lithography cost about $100 million. Very expensive. So the SIA means Semiconductor International Association. So So they have the roadmap for the IC production. So it's mainly driven by the scaling down of the feature size, and this is mainly realized by using more and more advanced lithography systems. So lithography consists of 3 steps. First is the mask design. We design the photo. So this is called the photo mask. So we have the layout, simulation, and the design rule checking. Then we make the photo mask. For the high resolution photo mask, it is made by electron beam lithography to make the photo mask. So low resolution photo mask can be made by the laser writing. So we use laser writing or electron beam lithography to make the photo mask. Then we do the exposure. So we have the mask, we do the exposure on the wafer. So now we look at the light source for the photolithography. So first, we use the UV light. So you may wonder, can we use visible light? Can we use visible light for the photolithography? So in principle, we can use visible light. And then the problem will be, so the resist. If we use the visible light, so the resist will be exposed inside the room by the room light. So this is a problem. But if we use the UV light, then we can filter out the UV light. If we look at the QNC building, the clean room, so you see that we have it's called the yellow room. You see the building, if you look from outside of the QNC building, so we have the orange color, a yellow or orange color of the windows. So this one is to filter out the UV light and also filter out some of the blue light. So if the blue light, if the short wavelength blue light is filtered out, then the room will appear like yellow. That's why it's called a yellow room. Or sometimes the color a little bit orange room. So we use the UV light. So traditionally, the UV light is made by the mercury vapor lamp. It is also called mercury arc lamp. So you have something like this. So you have the mercury vapor inside, and then you apply voltage. So we have the arc. We have the plasma. So we have the plasma in this glass container. Then the electrons are excited to the high energy, and when they come back, when they come back to the ground state, the light, the photon will be emitted. This is how the UV light is generated. So this is the spectrum of the mercury arc lamp. So we have the most useful one is the I line. So 365 nanometer is very, very useful. Sometimes H line and the G line is also used for the lithography. For the lithography in the quantum nanofab, quantum nanocenter clean room, so we have the I line, H line, and G line. We use this kind of lithography. So the light is not so stable, so we need routine calibration. That means we have the meter, we have the a photodetector, a kind of light meter to measure the light intensity from the lamp. Then we can modify the exposure time to get the right exposure dose. So this one is not expensive. $7 lasts about 1,000 hours. So this mercury arc is also used for the lightning. It's also used for the lightning. This is called a CF, compact fluorescent lightning. Compact fluorescent lightning. If you look at here, let me show you. So this kind of lightning here, but they are not so popular nowadays. It used to be much popular light. This one is also made by the mercury arc. So if you look at here, I think this one. Yeah, this is the principle of this compact fluorescent lamp. You can see. So we have the mercury atom inside, and we have the electrodes to ignite the mercury atom to form the plasma or arc. So we have the light. But this light is the UV light, ultraviolet light. So to convert UV light into visible light, so we use the fluorescent powder. We coat fluorescent powder on the wall. So then the UV light will be converted to the visible light by this fluorescent powder. So this is how the compact fluorescent lamp works. Nowadays we mainly use this is the compact fluorescent lamp. We have the mercury inside. This is LED light. This is the old style incandescent light. Nowadays, so people mostly use LED light. LED light is more efficient and lasts a longer time. But for the mercury lamp, this is the mercury lamp. So to have higher resolution, we need a shorter lambda. We want shorter and shorter wavelengths. But for the mercury lamp, shorter wavelength, you can see, for example, this 248 nanometer here, 248 nanometer. So this one is 248 nanometer. You see the light intensity from the mercury arc lamp is very low. So to solve this problem, we use the krypton fluoride laser. So this is the excimer laser. So those excimer laser give much higher light intensity at shorter wavelengths compared to the mercury arc lamp. So nowadays, so excimer laser is used for the lithography. So what is excimer? Excimer means excited dimer. It is a kind of dimer. So we have two components. So one is the noble gas. So we know the noble gas is the helium. So this is the noble gas. Another we have the hydrogen gas. So this one is fluorine, chlorine, bromine, iodine. So we have two of them. So we know that those noble gas, they are very inert. They do not form compound with other materials. But at excited state, In the excited state, they can form the compound. For example, here we have the xenon chloride. This one is not stable, it will fall apart, xenon chloride, because this noble gas cannot form compound with chlorine. But at this excited state, the star means excited state, it can form the compound. So we need some excitation. So we need some excitation energy to excite it. This is electrical energy to excite it, excited to the excited state. But this state is not stable. It goes to the ground state and emit the UV light. This ground state is not stable. It falls apart to two components. So this is the idea. This is the idea of the excitement laser. So you can see this is the example for the this one, krypton fluoride. So we have the krypton gas and the NF3 to form chlorine fluoride. This is the excited state, then go to the ground state, emit the deep UV light, and then from the used for the lithography. So nowadays, so the generator use 193 nanometer. So this is still the mainstream wavelength for the optical lithography for the IC manufacturing. But nowadays we also have this EUV. This is called extreme UV light. This one is 13.5 nanometer. Lambda is very short. So now today we use both EUV and 193 nanometer as the lithography tool for the IC manufacturing. So we will talk about extreme UV light next term in the NE. So in this course, NE343 that I will teach, we will talk about EUV lithography. So this is excitement lights. So all the excitement lasers, so they are paused. So I can ask you a question. Do you think we can look into the excitement laser? Can we look into the excitement laser? There's a pause. Actually, excitement laser is used for the surgery. So we can look in its surgery of the eye. I can show you here. So this 1 minute video will show that excitement laser can be used for the surgery of the eye, shine onto the eyes.
Excimer laser features a completely sealed nitrogen-flushed beam path that is checked in 3 separate locations for energy and consistency, thus setting the standard for both laser precision and durability. Pupil dilation causes pupil centroid shift, or a shift in the visual axis. The Wavelight EX500 excimer laser is able to compensate centroid shift and make necessary adjustments to align with the predetermined treatment profile. The Wavelight EX500 excimer laser maintains a high pulse frequency with a minimized thermal load, allowing only 1 in 5 pulses to overlap. This allows the treated area of the eye to cool before receiving additional pulses from the laser. This treatment algorithm provides a market-leading treatment rate of approximately 1.4 seconds per diopter. Designed to automatically track movements of the eye with a latency time of just 2 milliseconds, the Wavelight EX500 excimer laser automatically adjusts pulse placement to provide patients with exceptional precision and safety.
So this is the summary of the net source for the lithography. So we have the mercury arc lamp, so 436 nanometer this G line, 405 nanometer H line, 365 nanometer I line. Then we have those excimer lasers, krypton fluoride, argon fluoride, and fluorine. So this one, as we know, is 248 nanometer. 193 nanometer. So this one is skipped, is ignored nowadays. This one used to be a popular choice of the next generation lithography, but about 20 years ago, 157 nanometer, this one is given up. So all the light, so they are paused. The pulse length is nanosecond. It's about 20 nanoseconds. That's why we can do the eye surgery. We see the video for the eye surgery because the time is only nanosecond, so only about hundreds of nanometer of the skin. A few hundred of nanometer of the skin of the eye can be burned. This is how the eye is corrected. So each pulse burn away about hundreds of nanometer of the skin or of the tissue in eye. So otherwise, if we use the continuous light, then it will burn the eye. So now let's look at the photomask. So for the mask, so we have something opaque on top of the transparent material. So opaque material is chromium. The transparent material, this one is glass. It's glass. It can be soda lime glass, that's cheap, or quartz glass. So quartz glass has lower thermal expansion coefficient and lower absorption of the light, but they are more expensive. So normally for research, we can use the soda lime glass for the photo mask. So we can also use the transparency by the laser printer. So nowadays people don't use transparency, don't print transparency very much. In old times, so people use transparency for the presentation. So this is what we have the black color on top of the transparency. This can also be a mask used for the mask. So the resolution can be down to a few micrometers. So why we use chrome as the mask? So why we use chrome? So first, chrome is hard. If you use gold, gold is soft. If you do the scratch, if you scratch the gold will be scratched away. But chrome is very hard, very hard metal. It cannot be scratched away. Secondly, chrome is very chemically stable. For example, no acid or base can remove chrome, can dissolve chrome. So because the chrome, they form a very stable chrome oxide layer on the top. That's why actually for the stainless steel, so what makes stainless steel is because they add the chrome. If you add the chrome into the iron, then you get stainless steel. It's very, very stable. So no chemicals, no acid, no base, no solvent can activate the chrome. But chrome steel can be etched. It can be etched by a mixture of different components, but not by a single acid or single base. So here is the chrome agent. So we use a lot of chrome agent in the lab because we pattern chrome very often. So you can see, so this is the chrome agent. So we use a mixture perchloric acid. So this one, perchloric acid, this one can be replaced with the nitric acid. And the stearic ammonium nitrate. So this one. So this one is the unique. So this one has to be like this. But this one, the first one can be replaced. So this is the chemical reaction. So normally, it's obvious. So we don't have this mixture. We don't have this mixture by chance. So we cannot. So when we clean a wafer, the chrome will not be removed. When we clean a mask, chrome will not be removed because we don't have this thing in the cleaning procedure. So this is a chrome mask. That's why we use chrome as the opaque material. So for the polarity, so it can be a light field like this. So most area is transparent, some area is opaque. It can also be a dark field. Most area opaque, other area is transparent. So which polarity to use depends on what tone resist you use. For example, a positive resist with light field will give you the same pattern as negative resist with dark field. So we can do something to improve the photo mask, photo lithography. For example, we use a pellicle. I will talk about this next slide. Anti-reflection coating to avoid light reflection. This will also be covered. And phase shift mask. This one we will learn phase shift mask next term in the NE343. So now we look at the pellicle. So why we need a pellicle? So pellicle is a kind of a film, a plastic film on top of the chrome mask. So you can see, so here is the chrome. This is the photo mask. So here, 1 centimeter. So we have 1 centimeter on the top. So we have this pellicle film. So this is a plastic film. So why we need this plastic film? Because, for example, if we have a particle dust, if a dust particle, it fall on the pellicle, this is not a problem. But if they one fall on the chrome surface, then the exposed pattern will be this one will show up on the exposed pattern. But if it is on top of this 1 centimeter away from the chrome mask, then it is outside of the focal plane. So it will not form image. This is something like, for example, if you put some dirt on my glasses, I cannot see it because it is not, my eye is not focused on my glass. This one is very critical. Otherwise, the chrome mask, if you have one dust on the chrome mask, then this mask will be dead. So it always gets pellicle film. So the mask is also called a reticle. This word reticle. Reticle means photo mask. Photo mask is IC word for the photo mask. This one is to distinguish. We also talk about. We all know about etching mask. So here is the photo mask, etching mask. To distinguish the etching mask, then people call it a reticle. So now let's look at how to do the alignment. So alignment is utilized by something called alignment mark. Alignment marks. For example, in this case, first when we do the first exposure, so we pattern this part. We pattern this part. We pattern this the dark color part. So this is alignment mark. This is on the wafer created from the previous exposure step, from the previous process step. Then on the second exposure, the mask. So the mask has an opening. This is the opening. The left color opening. Open window. This open window. So from this open window, we can see the previous alignment mark. This way, we move around. We can have the alignment. We move around. We can have good alignment. We can also use it's called a vernier pattern for the alignment. This is why, for example, if you see the symmetric like this, you know it's well aligned along the X direction. So for the snipers, we have automatic alignment. Because we have the optical system that can look at the alignment mark and look at alignment mark on the wafer and also alignment mark on the mask at the same time. Then you can do the automatic alignment. For the lab, for the research equipment, this is normally what we do. So we have two optic mark scopes, and we have one mark on the left, one mark on the right, and the image, this for the image on the left, and this one is for the image on the right side. If we see like this, then we know the wafer. We do the rotation and the movement of the wafer until we see like this, then we know they are well aligned. So you will do this kind of experiment for the lab course. So one problem with the alignment is the thermal expansion. For the thermal expansion, for example, if we have a rod, the length is L. So when we have temperature become increased, so the rod will become longer. So this is third L. So when we have higher temperature, it will expand by third L. So third L equals alpha delta T. So this is the basic equation for the thermal expansion. For the case of the photolithography, so we have the thermal expansion of the mask, and we also have the thermal expansion on the wafer. So then this is called the run-out error misalignment. This is called misalignment equals R is the wafer radius, alpha delta T. So this is alpha delta T. This is the mask, and this is the silicon wafer. So now let's estimate how much mismatch will be induced by this thermal expansion. For example, the silicon has the thermal expansion coefficient 2.6 part per million. ppm is part per million per degree. So quartz has 0.5. Then the difference is roughly about 2. If we take the alpha here, 2 ppm per degree. So we have 1 degree temperature difference and 1 degree temperature difference. Then the distance between the two marks is 50 millimeter. So 50 millimeter times 2 ppm per degree times 1 degree. Then this gives you 100 nanometer. So this is okay for research. This is not a big problem. But for the production, for the IC manufacturing, we know this is a big number. Nowadays, we have like a 5 nanometer node. 5 nanometer node for the commercial production. This 100 nanometer is too much compared to the 5 nanometer feeder size for the IC manufacturing today. So that means in the clean room environment, the temperature needs to be very, very stable. I think it should be better than 0.1 degree. If we have 0.1 degree, this 100 nanometer become 10 nanometer. Then we have 4 times, we know reduction, right? So we will see there is 4-time reduction by the length. So after the reduction, so this becomes 2.5 nanometer. So if the temperature stability is much better than 0.1 degree, so it should work. So now let's look at photolithography systems. So normally the easiest way to do the lithography is you put your mask. You put your mask on top of the photoresist, which is on top of the silicon wafer. You shine the light, you put the mask, this will be done. So this is called a contact printing. We have no gap. So the good thing is that this one gives you a very high resolution, but there is the mask wear out and defect because there is contact. The mask will be worn out. To solve this problem, we can have a gap. We have this gap. Here is the gap. We have this gap. So this is called a proximity printing. So then there is less mask wear, but the resolution will be worse. So third one, those two actually the same instrument, and for the instrument in the clean room in the university, we use this kind of lithography. They are the one system that can do both. You don't make the gap or no gap. So the third one is called projection lithography. So this one is mainly for the production, not for research. So in this case, you have the photo mask. On the other side of the lens, this is the lens and this is the wafer. So effectively, the lens projects the image of the photo mask onto the wafer. So this way, the mask will never be no wear out and no contamination because the mask is on the other side of the wafer. And we can also do the 4-time reduction. 4-time, that means the image size, the feature size here. So the feature size here can be 4 times smaller than the feature size on the mask. So this makes the mask manufacturing easier. So we have the lens. When we have the lens, we can do this 4-time smaller feature size. So now let's look at the first. We look at those two systems. It's like this. So we have the mercury arc light. It's always mercury arc lamp. But nowadays there is also LED light. But usually it's still like mercury arc lamp. Then we have this collector lens, a mirror. Number 4 is the collimator and some filters, ND filters, some filters, another mirror, another lens. This is the condenser lens. Here is the mask. So this is the optical setup for the lithography system. So how about the resolution? If we look at here, so you can see the smaller the wavelength, the higher the resolution, and the smaller the gap, the higher the resolution, right? This makes sense. Smaller wavelength, higher resolution, smaller gap, higher resolution. So in the end, so R is roughly given by lambda G. So lambda is the wavelength, G is the gap, R is the resolution. But if you want to be more accurate, it is this formula here. R equals 3/2 square root lambda G plus T/2. So this is the thickness of the resist. So effectively, here is the chrome mask. This is the chrome part. So here is the wafer, here is the resist. So the gap here, the number here, G plus T/2 is from the chrome mask to the middle of the resist thickness. This also makes sense. Now this is the resolution for the proximity exposure systems. Now this is used for the research. So we have, I think in this university, we have maybe 5 to 10 lithography systems like this. The next one is called the stepper. So stepper is used for the IC manufacturing. So in this case, so we have the light source. This can be the excimer laser. Now it is excimer laser. Then we have this alignment laser. So we use this laser to look at the mask and also look at the wafer for the alignment. Then we have the reticle. As we know, the reticle is the word. It's photo mask. So this is the IC word for the photo, just photo mask. This is the photo mask. Then we have this condenser. It's called the projection lens. Then we have the wafer. Each spot we have the die by die exposure systems. So each time we expose one die. So each die about 2.5, I think 3 roughly. So each of the die is 2.5 by 3.5 square centimeter. Yeah, this is the production lithography. There is also called a scanner. In the case of a scanner, the entire die is not the entire die. Each die is not exposed at the same time. So if this is the die, if this is one of the die, exposed like this. This is called a scanner. I uploaded the video silicon run lithography. So you can see the scanner in the silicon run lithography, the video. Okay, thank you.